Okay, I'm going to go through section B questions of this Physics International A-Level for Unit 4 Physics, Further Mechanics, Fields and Particles. We went through the multiple choice questions earlier. This exam was a first exam with the post-COVID grade boundaries. The grade boundaries are higher. Make sure you check that out when you are testing yourself with this unit. Grade boundaries are much higher than the ones given in January 23 and before. Don't forget to like, share and subscribe as requested before. It really helps the channel. It's a new channel. We started it last January and we're looking for 1,000 subscribers as soon as possible so we can monetize the channel. Your help is needed. Thank you. All right, so questions 1 to 10 we've done. We're looking for the section B, and the first section B question is about particle physics, and it says in CERN in 2022 they announced the discovery of a new particle known as a pentaquark, okay, which is made of 5 quarks. Of course, these strange particles don't exist for long because they're not stable. That's why they don't exist commonly. And if you understand particle physics, the whole idea is to see how matter came to be the way it is today. And to do that, they need to put a lot of energy into matter to see what happens at higher energies, which is kind of like the beginning of the Big Bang period, where the energy was very intense, the universe was much smaller according to the Big Bang theory, and there would have been a much higher temperature, and temperature is to do with thermal energy and movement of particles. So when they collided with high energies. So the table, it says, shows the charges on some quarks. Up and down are first generation quarks, which is what most matter is made of in the current period of the creation of matter. And then S and C quarks, strange and charm, are the second generation of quarks which were discovered to exist at higher energy states. Okay. It then says that the 5 quarks in the pentaquark that they discovered were made up of one charm, one anti-charm, a down, a strange, and an up. Okay. So I put the charge of the anti-charm particle in the table next to the charm particle. So the anti-charm particle will have the same mass but the opposite charge. It says some scientists said the pentaquark is made of a meson, which is a quark anti-quark composition, and a baryon, which is held together by the attraction of their equal and opposite charges. That means one of these particles, the meson, must be of one charge, and the baryon must be of the opposite charge. Okay? So how can we get these 5 quarks into opposite charges? So you've got to determine the quark combination and the charge of the meson and the baryon that could make up this pentaquark. So I've put that you could have the charm, anti-charm, because you need the antiparticle to be part of the meson, and I wanted to give it a negative charge because I know that protons, for example, which are baryons, are made of positive charges. I'm going to make my 3 quark particles positive, and my anti-charm must make a negative particle, so I want to have a -2/3 and a -1/3 to go with it. So I've put anti-charm with down, and that would give me a negative particle. And then I could equally have put the anti-charm with the strange, and depending on which one I choose as a student, for example, I then have to choose the other 3 quarks that are left from the pentaquark 5 to be able to work it out. So either you do anti-charm down or anti-charm strange. Both would create a negative charge on the meson, and that would leave for the um, baryon, yes, you want it to be positive. So if I'm using the CD combination, anti-CD combination, look at the arrow is going to CUS or left, yes, because you have to use what's left, and that would create a positive charge because charm is plus 2/3, up is plus 2/3, and strange is minus 1/3. That would give you the CUS combination for the baryon of a +1 charge. So if you do the C bar D combination, you need to then in your second answer put the CUS combination. In other words, you can't just have whichever one you want. You've got to combine your answers. On the other hand, if a student had worked out that you could have the C bar S combination, then the baryon must be the CUD. There is a third combination that you could create, which would be SUD, yeah? And if you did that, an SUD would produce a neutral charge, so it would not fulfill the obligations of this question. So it must be the ones in square brackets, and it must be combined with the correct meson combination. Hope that makes sense to you, and that's where you get the marks, okay? So you want the charge to be negative on the meson and the charge to be positive on the baryon, and they must complement in terms of the total number of quarks that you start with. In other words, you've got to use each of the quarks once. Okay, that's question 5. Question 6 is a particle with charge Q and momentum P given to you that follows a circular path of radius R, and the path is at right angles to a magnetic field of flux density B. Now, if you look in your equations, you will find, I'm just going to have a look, if you could look at the back of your exam paper. I don't have a physical copy with me, so I'm just looking on a digital copy to see that there is an equation which you need to get used to, yeah, for which looks a bit like the one that they want you to derive. So when you have an exam question, you want it to be very familiar with the equations on your equation sheet. And if you look right at the bottom of the equation sheets for Unit 4, you'll see in a magnetic field that that equation is given to you. But they want you to show where it comes from. And basically, in a magnetic field, a charged particle will undergo circular motion. Therefore, there must be a centripetal force, which is mv squared over r, which is equal to the force due to the magnetic field, which is bqv, which is what I've written. You'll excuse my handwriting, or because I wrote small q at first, and I've changed it to a big Q in corrected the purple pen into red. So mv squared over r must equal, yeah, so mv squared over r must equal bqv. So the middle letter in the second box is q. Okay, hope that makes sense to you. Then all you've got to do is rearrange it for your 2 marks and make r the subject of the equation, and you'll see that it's easy to derive the equation that's given to you in the exam on the formula sheet. Hope that makes sense. So that's where you get the 2 marks. So it's the centripetal force equation derivation. It then says that the particle is an alpha particle with an energy of 5.4 mega electron volts. Remember, like in the multiple choice question, we know that we have to convert electron volts into joules, and this is a very common question. You learnt about this in Unit 2, that electron volts, converting it into joules. You've got to multiply the 5.4 mega, which is 5.4 times 10 to the 6, by the charge of an electron. That's why it's an electron volt. Yes, it's basically the kinetic energy an electron would gain if accelerated by that voltage, 5.4 megavolts, yeah? So you multiply the voltage by the charge. Charge times voltage is energy in joules. That's why it gives you a value in joules. So that's where E equals QV comes from. When you do that, you will see that the energy will come to 3 significant figures as 8.64 times 10 to the minus 13 joules. The mass of the alpha particle is given, yeah, and they want you to calculate B. Okay, so once we know the mass and we know everything else, the equation that's given to you in the exam is kinetic energy in the form of momentum. So you can make sure you know where this equation is on your equation sheet. The P squared over 2m is basically the same as half mv squared, and if you're not familiar with that, you need to go and revise the chapter where they show you this is another way of writing kinetic energy. So because we know the energy is given, we just worked out from E equals QV, we know the kinetic energy, we know the mass, so we can now work out the momentum. And once we know the momentum, we can use it in the derived form of the equation from part A. So we're missing the momentum is P. Once we work out P using the energy and 2m, you can see that it gives you an answer of 1.07 times 10 to the minus 19 momentum units, which is kilograms meters per second. And then once you know that, you can use the equation which we derived in the part A, P over BQ, where P is momentum, yeah? So now we know P, we can put the value in the equation from above to work out B when we change the subject to the equation, yes? So we want to make B the subject of the equation, yes? And if you do that, you'll find that you'll get the equation in the box where the arrow is showing you, yeah? So B will be equal to the momentum divided by Q divided by R. So we know the momentum is 10 to the minus 19 in it. You know the charge has a 10 to the minus 19 in it, so you can cancel out a 10 to the minus 19 to save you a bit of time, and you come up with the answer of 3.48 Teslas, yeah? And I think in this question you want to keep 3 significant figures. You can round it up to 2 significant figures should you wish to, because some of the values are given to 3 significant figures, but most of them are given to 2 significant figures. So I think you're quite valid in changing that to 2 significant figures. If you look at the mark scheme, which is available now because this is May 23, so they usually release the mark schemes 12 months later, you will be able to find there's an alternative method where you can use the normal kinetic energy equation, but it will take you a bit longer to do it, okay? Have a look at that to see that you can get the same answer. So that's question 12 done. Question 13 is also about particle physics, yes, which is why all of these topics are together. The further mechanics, the circular motion, because in a magnetic field you do get charges accelerating in circles where they're going, but in this case now you've got a linac and cyclotrons. It says both accelerate charged particles to very high speeds. The diagram shows a linac, and you'll notice that the linac is a linear accelerator, and the particles go through gradually longer and longer tubes called drift tubes, and the charges are then accelerated in between the drift tubes, okay? And you'll see that there's an AC supply that controls the voltage changing periodically to synchronize the voltage to attract the charges which are going through the drift tube. So as soon as they come out, the tube in front will be synchronized to be the polarity that would attract and therefore further accelerate the charged particles that they want to use in the linear accelerator. So you've got to explain the use of electric fields in the linear accelerator or the linac. Okay, you should refer to the frequency of the AC supply. So the particles are accelerated by the electric field by the electric field in the gaps. So the electric field is in the gaps, and I've drawn that as arrows in a diagram that they've given you. Okay, so the charged particles accelerated by electric fields in the gaps, as shown above. I've written the AC frequency is constant, yeah, as most AC frequencies are, so that the particles spend the same time in each of the tubes, yeah. So I should have put they spend the same time in each of the tubes would be more clear for students learning this theory. This is achieved by increasing the length of each tube, so you know that there's a constant frequency, there's a constant period. For that period of time, you want the charged particle to be inside the tubes, and then as soon as the frequency flips, so the polarity of the drift tube in front of the particle becomes, say if it's an electron, it would become positive. The electron will experience an accelerating force in the gaps between the drift tubes as it exits. And to make sure that the charged particles stay in the tubes for the right amount of time, they make the lengths of each successive drift tube longer and longer to ensure that the time times the velocity can be used to calculate the distance or the length of each successive drift tube. Hope that makes sense. And this is a 4-mark question, so this could also be a 6-mark question in another paper. So the polarity of the AC, and hence the electric field, is synchronized to ensure it is always creating an accelerating force on the particles in the gaps. And that's how you get the 4 marks for this question. Okay, this will be repeated in most exams, some kind of question on linear accelerators or the cyclotron. So you need to know how each one uses frequency and what is constant in each one and what needs to change, and how they synchronize the motion of the particles with the frequency of the AC supply. So that's part A, and then part B is on the cyclotron. So the cyclotron is a circular version, again with the AC supply, and this time the gaps are between the 2 halves of the circular path, almost circular path, 2 Ds they're called because they look like capital Ds, yes, and gradually the charged particles, as they accelerate, their radius of rotation increases, yeah, so they start at the center and they just spiral outwards, and their paths, their time in each D is synchronized to match the AC supply frequency, okay? And it says explain why a magnetic field is applied at right angles to the Ds in the cyclotron. So the 2 Ds in the cyclotron, as you can see from the diagram, the 2 Ds are shown, and in between you've got an AC supply to make sure whenever the charged particles go from one D to the other, yeah, they are accelerated by the electric field between the 2 Ds, okay? So explain why a magnetic field is applied at right angles to the Ds in the cyclotron. Well, that's to produce a centripetal force needed for the circular motion of this spiraling path as the electrons, or the charged particles, doesn't have to be electrons, gain kinetic energy or speed. So the particle experience a force at right angles to their motion in a magnetic field, and that is why you need to make sure you are following Fleming's left-hand rule and that they're going in the right direction. Okay, so the field will be at right angles to the direction of the movement of the charged particles. Okay, and I think that will be a good place to stop. We've done 3 of the short section questions, and the next question is on looks like it's going to be on conservation momentum. So I'm going to start the next video on conservation momentum. Hope you found my answers clear, and please don't forget to like, share and subscribe so you know when the next video is going to be uploaded. Thanks for watching. Bye for now. See you in the next video.